last class, if you recall, this is the stencil or unstructured cell we were looking at. We were looking at, okay, how to do finite volume integration over this control volume. Okay, that one. That's our cell of interest. And what we said was, okay, we have this term that we are trying to discretize. This is the main term. If you recall, our finite volume formulation had summation over faces, gamma f, AF being the area, grad phi f dot NF is equal to S naught times V naught. Okay, that was the finite volume equation that we got out of Gauss divergence theorem. And so we said, okay, gamma f we calculate by interpolation, area of the face we know how to calculate. So this is what we are trying to express in terms of the cell center values of phi. And last class we did this decomposition into normal and tangential fluxes, and we said, okay, this is one term we get, which is sort of second order accurate if the mesh is uniform. Okay, so that's basically this phi minus that phi. That's what you have here. And then we end up with this term, which is really your tangential flux term. Okay, so that's we are going to write that as just JT to indicate that it's tangential flux. So let's talk about now how to approximate that term. Okay, so first term on the right hand side of this expression has cell center values, so we don't need anything, so we are going to reduce this second term. Okay, now earlier we derived this, we said, okay, something like grad phi f, okay, dot L being this vector connecting the two cell centers, we expressed it as phi 1 minus phi naught. Okay, so that phi minus that phi. We did the derivation in the last class, so you can go back and look at it. Okay, so another way of writing that is saying that, okay, the L vector is nothing but the magnitude of the L vector times a unit vector in the L direction. Okay, so we can write it as that, and therefore we can say grad phi f dot the unit vector L is phi 1 minus phi naught over the magnitude of L. Okay, that's another way of writing it, right? This is equivalent to that expression, except that here I have the actual L vector, here I have the unit vector in the L direction. Okay, same thing. So similarly, we can extend that to now another vector. So we can say now grad phi dot t, t being the tangent as shown here, okay, is that value minus that value divided by the magnitude of the tangent. Okay, so exactly the same. We're sort of drawing an analogy here because both are L and T are vectors, so it should be applicable to any vector. Okay, so everybody follow that? So it's kind of like a finite difference type of formula, as you can see. It's just saying that value minus this value divided by the length. That's what that quantity comes out to be. Okay, so therefore my JT becomes that. Okay, so I'm just substituting this expression in here. Okay, so that's my JT. And now it's a question of how do we calculate each of these guys. Okay, now TF is the magnitude of the tangent, which is nothing but basically this length. Okay, and that length in 2D is nothing but the area of the face. All right, and then TF dot L, you simply take the T vector and the L vector and dot it. That's all this is doing. So it's taking, so your T vector is XA minus XB I plus YA minus YBJ divided by the magnitude of that vector, because this is the unit tangent. Okay, and the L vector is X1 minus X naught I plus Y1 minus Y naught J. And so you dot the two, you get this term. Okay, the division by the area is because I'm converting the tangent to a unit tangent. Okay, and AF is nothing but the length of the tangent. All right, so it's just a simple geometry calculation, direct dot product. All right, so once you are at that face, you already know the vertices of the or the coordinates of the vertices. Okay, so first of all, from the face you can figure out what are the two vertices of that face from the connectivity information. Once you have that, from that you can get the coordinates of the two vertices, which will be your x and y at A and B. Okay, and then you also know the vertices of the cell centers 0 and 1, so you can do this calculation directly. It's just a geometry calculation. So combining the results, this is what our normal component of the gradient of phi comes out to be. This is what we had derived last time. This is what we just derived, okay, where Tf dot L is that guy on top. Okay, so now I'm just making a note here that this L is actually for one particular face. In general, this should be LF. That is, you're going to go around, from phase 1 to phase 2 to phase 3. We have just done the derivation for one phase. Okay, so these guys will all change. For example, this phi 1 will be replaced by phi 2, okay, and phi 3 for the three individual phases. This delta will be replaced by the corresponding delta for these two guys. Okay, similarly the L will get replaced by these vectors. So that's what I'm saying here, that those are local quantities for that phase, the delta and the L. Okay, any questions? So once I plug all that, so this is my overall expression, and now here I've put in the phase index just to make sure that it's local to the phase, and I plug it in there. So this expression will get plugged in here into my finite volume equation, and this is the final algebraic equation. Okay, so final algebraic equation, right hand side is still as same as Cartesian mesh. Here you notice that you have phi of the neighboring cells. Okay, we haven't assigned a number there because we don't know the number a priori. We have to basically go to each face and then ask or query what is the cell number next to that face, and then accordingly put it in, okay, into that equation. And then here is your tangential term. But this is the overall finite volume equation that you would have. As we discussed last time, if your mesh is such that the normal and the L vector are aligned, then this guy will be 0, the T dot L, and this tangential term will disappear, and you are back to basically square one, meaning whatever you had for a Cartesian mesh. Okay. Any questions? So, and as I said, next class I will show you a little code where all this is calculated, and you will clearly see from this equation how we get to the matrix coefficients. Okay, but it's kind of easy to see. And so let's now talk about the treatment before we even move forward. How do we treat these guys? So our original goal was to express this in terms of cell center fees. Okay. But we have only partially succeeded. Why? Because only in this term we have cell center fees. This term has vertex values of phi. It doesn't have cell center values of phi. These are vertex values, these two. Okay? It's only sort of partial success. We have expressed it algebraically in terms of phi, but not necessarily cell center values of phi. So then the question is, what do we do now? Okay? And then there are two ways of treating this term, this tangential term. Okay, one is what's called the implicit method. So in the implicit method, what you do is for example, you would write phi a, the value of phi here, in terms of using your interpolation functions, cell center values of phi. So this guy would be expressed in terms of that guy, that guy, that guy, that guy, and that guy, 5 other cells. Okay. Similarly, phi b would be expressed in terms of these 5. Okay, and then you can plug it back in here and in here. Then you will have a complete equation in terms of cell centers. Okay, that's the implicit treatment. So the advantage of such a treatment is that, or the disadvantage of such a treatment is that now, instead of having, if you think about it, okay, if I go back to, well, let me look at this figure here. So suppose I'm trying to develop a finite volume equation for that node with just this term, okay, my equation would have 4 terms in it, okay, 3 neighbors and the cell center. Just like your Cartesian mesh, you had a 5-band system because you had 4 neighbors and the center, okay. But now when you do this and you extend your stencil to include, you know, all these guys, then now you have basically an equation with 11 non-zero terms, okay. So that's one of the disadvantages, because what you're now doing is you're reducing the sparseness of your matrix. So you need to store more coefficients, obviously, okay. That's one disadvantage. So it'll have 10 off-diagonal terms as opposed to only 3. If you do this kind of a treatment. And in 3D, it can go even much more beyond that. You'll typically have 25, 26 off-diagonal terms. Okay, still very sparse. I mean, if you think about thousands of nodes, 26 out of 1,000 is really nothing, but still you have to store quite a few numbers. Okay, the other big disadvantage is boundary conditions become difficult. Okay, which you can see now. If this was, let's say, a boundary face, I would use typically this guy, and this guy. So my equation would have only 3 terms. But now if I start including additional terms, then things become very complicated, because now you're saying, okay, now what do I do with that guy? Those are boundary nodes. Okay, how do I treat that implicitly? So that becomes a challenge because your stencil gets extended. So very rarely people actually do implicit treatment for the tangential flux. Typically what they do is explicit treatment, and what that means is you express the vertex values in terms of old iteration values, because you know that I'm ultimately going to solve the system of equations using an iterative solver anyway. Okay, so why not just use old values there? And if you do that, then basically this is what happens. This term here, okay, for example, you have these 3 terms arising out of that, phi, a, b, and c, but they are at old iteration values. Okay. So since they are at old iteration values, they have been put on the right hand side of the equation. Okay. And on the left hand side, we only have the major normal components, or the components along the L vector. And those have just phi naught, phi 1, and phi 0, phi 1, phi 2, and phi 3. All right. Everything else has been pulled over to the right hand side. Now, of course, the disadvantage of the explicit method is that your convergence could be poor, as you all already know. Okay. So rearranging the equation, this is what we get, and here are our matrix coefficients now. Okay. So here's your A naught, your diagonal. Okay. Here are your neighbors. Okay, and here's your right hand side vector. So right hand side vector has this new term which we are calling the skew source. The skew source is nothing but this whole term. Okay. So later on, when I show you a code, you will see what is the way this is typically coded in is, you go over all cells. Whenever you visit a boundary face, you simply set the neighboring coefficient to 0, okay, because that term you're going to add as a source later on. All right. So suppose I am at a cell like that, and this is the boundary, okay, and I'm looping over all the faces. For this face, I'm going to store my neighbor, okay. And then for this face, I'm going to store my neighbor. For this face, I'm simply going to set my neighbor to 0. Instead, what I'll do is I will later on, add the contribution of that face as boundary condition, which I will show you later when we discuss boundary conditions. Okay, and then because of the tangential flux, this will get added to the total source at the very end. So what you will do is if you think about the way you've been setting up matrices, you store your diagonals, you store your off diagonals, you store your source terms, and then you call another function which calculates this skew term and just adds it to the source term. Okay, and it's very easy to test if you make the mesh Cartesian, that should automatically come out 0, no matter what distribution of phi you have, because these guys geometrically are 0. Okay, that's one way to test it. Any questions? So it's not as difficult as it seems. You have to do a lot of work on paper. Okay, the difficulty really is in processing the mesh. The difficulty is not in the finite volume implementation itself. Okay, it's just a question of calculating an additional term, which is not that difficult. I mean, of course, you're doing more complex geometry now, so you have to pay a price. It's not going to be as simple as a Cartesian mesh. So there is some work to do, no doubt about it. But really, coding in this is not as difficult as having to process the mesh and process all that connectivity information and getting everything ready to be able to code in those terms. Okay? So if you look at the code, you will see 80% of it is processing geometry. 20% of it is actually, these terms. Okay, so this is the basic outline. Now, one thing I should mention is, in terms of the structure of your matrix, for a structured mesh, you had these nice banded structure. Now, here is what you're going to get. Okay, you're going to get still a sparse matrix, but these coefficients scattered all over the place. In every row, if I denote the diagonal by a circle, there is no particular order where these elements or non-zeros are going to be. Okay, they could be anywhere. Only thing you know is how many non-zeros you're going to have. Okay, so it's still a sparse system, but there is no structure, no bandedness to it anymore. Okay, so one of the things that happen now is you can't use solvers like ADI, Stones, all the ones that rely on the banded structure. You can still use some of the more powerful ones like multigrid. Well, geometric multigrid would be very difficult, but you could still have, like a structured mesh and treat it like an unstructured mesh and still do geometric multigrid. Okay, you can definitely use conjugate gradient. Okay, and of course Gauss-Seidel and all the point solvers. Okay, so that's the idea. Now, one thing I should also mention is that the way these guys are stored, okay, are not in the form of, again, a square matrix like this. So the way these are indexed are, you would typically have A naught as a function of the cell number. So that's just one big one-dimensional array, IC going from 1 to total number of cells. Okay, and then you would have this A neighbor, which would be indexed IC times number of faces of the cell IC. Okay. Now, depending on the computer programming language you use, there are programming languages which will allow you unstructured data structures. In other words, if you imagine, let's say this guy, this is of length, let's say 1 million, okay, 1 million cells. Now, this guy could be either 3, it could be 4, it could be 5, it could be 10, depending on how many neighbors it has. Okay, so there are programming languages like C or C++ or even Fortran 95 which will allow you this unstructured data structure, which means that for IC equal to 1, you may be able to just allocate 3 slots. For IC equal to 5, you may be able to allocate 7 slots. So in other words, you're not doing 1 million times this maximum number 10 as your storage. You're going case by case for each cell. Okay. But at the worst case, you will have 1 million times 10, that much storage. Not 1 million times 1 million. Okay. So this is how this is stored, the neighboring cell coefficients. Okay. Now, of course, we know for each of these, from the connectivity information, we know which are the neighbors. Okay. That's something you have to know. In other words, you know the exact location of these slots where those non-zeros go in. All right. Any questions? Yeah.
Is there any algorithm or a method to number the cells in a way that is more banded, the matrix?
More banded?
Yes.
Yeah, people have tried that. It's very difficult to do because, especially in 3D, it's almost impossible. Okay, and the thing is, even if one element is beyond the banded structure, that's it. Your algorithm is out the window. Okay?
I mean, in finite element, they do that, right? In finite element. So number in a way that is
In finite elements, again, that depends. It's because of the way the formulation is. It depends on the shape functions you're using. Okay, so if you're using a consistent order of shape function everywhere, then yes, you are going to get a banded structure. But suppose I use a 4th degree polynomial here and the 3rd degree polynomial here, then you've broken it. Okay, and then the ordering of the cell also matters there also. So the problem is that, I could have a structure where everything is almost banded, but one element is out. Then that's it. You've broken the whole structure. Okay. So that's one of the problems. Now, mesh generators do try to make an effort to keep things clustered in the middle, not spread out too much. Okay. So, all said and done, you're never going to create a mesh where let's say I have a mesh here like that, if I, let's say, even have a Cartesian mesh like that this is cell number 1 and that's cell number 2. That's hardly going to be the case. Okay, they are going to try to number it like 1, 2, 3 and some order. Okay, even if it's a triangular mesh, it depends on how the triangles have grown, how they've grown the triangles. Okay, typically when the order faces, they do all the boundary faces first, and then they would go. So suppose it goes 1, 2, 3, 4, and then it would go 5, 6, and so on up to the total number of boundary faces. Then it would go this one, that one, that one, and then all the vertical faces and so on. Okay, so there is some order, but you can't guarantee any order. Most importantly, when you are writing the code, you have to assume that there is no order. Otherwise, it gets very difficult. Any other questions? Okay, so let's move on, and as I said, this is something we'll talk about more in the next class. So here are the steps to solve this system of equations, or to basically use the finite volume method for solution of an equation of a PDE. So you start with your guess for phi, same as before. Give your link coefficients, which are your A naught, A and B, the right hand side vector, Q naught, and so on. You calculate your vertex values by interpolation. That's a new step we are adding now. Okay, this guy is a new step we are adding. We wouldn't have to do that in a structured mesh or a Cartesian mesh formulation at all. Why? Because we are getting ready to do this calculation. Okay, and again, you need to do it in a modular way. You don't want to do that locally and calculate vertex values again and again locally. You just want to call one function which will calculate vertex values for you. Okay, and the advantage of that is you can feed in any data structure. So suppose here I'm calculating vertex values of phi. Okay, now suppose I'm solving the Navier-Stokes equation. I have 3 components or 4 unknowns, u, v, w, p. All right, 3 velocity components and pressure. I want to write a vertex value evaluator such that I feed in the u array, it gives me back vertex values of u. I feed in the v array, it gives me back vertex values of v. I shouldn't have to write separate, code for each one. It should be modular such that I just feed in any cell-based data structure, it gives me back vertex values. Okay, there will be some exceptions because u may have a different set of boundary conditions than v. So when you visit the boundaries, things may change depending on the variable for which you are doing the interpolation. But for the interior cells, there should be no difference. Okay, so this guy should be a self-standing modular entity. Okay, and then you calculate your skew sources, and then you do your iteration, whatever method you choose, Gauss-Seidel or CG or any of the unstructured solvers, and then you repeat the process until convergence. Okay. Now here's the thing: what people do is they don't often, or in many cases, they don't do this skew term calculation every iteration. Okay. So what they would do is they would start the calculation. They would maybe, if you think about, let's say now you're using Gauss-Seidel as your solver, you would do 5 or 10 iterations of Gauss-Seidel, and then you would update the vertex values and the skew sources, and then do another 5 iterations. Okay, so it's interspersed. You're not doing it every iteration, because if you do it every iteration, it's pretty expensive. These interpolations and skew source calculations. There's a lot of calculation there. Okay, so people often do it, especially for linear problems. It works great, updating the skew sources once in a while instead of every iteration. Okay. Any questions before we move on? All right. So points to note, I'm just repeating here a little bit. The explicit approach and the implicit approach are identical if the n and l vectors are co-aligned, and in that case, basically the tangential terms and the skew source is 0. Okay, and such a situation, I talked about this last class or the class before. Is manifested in a perfectly orthogonal mesh, as we have seen thus far, and also equilateral triangles or equi-area tetrahedrons in 3D. Okay, so you can clearly see here. Here's my L vector, and of course my N vector is aligned to that. Okay, same thing here. These are perfectly aligned. Okay, so and unstructured mesh generators, triangular mesh generators, actually they use that as one of the criterion for growing their triangles. Okay. They try to keep it as equilateral as possible. It's not always possible, of course, but they would try to generate as many equilateral triangles as possible if the mesh generator is a good one. Okay, now there are some crappy ones where you will see really bad triangles sometimes. Okay, but generally the good ones you will see if you take, let's say, a square domain and just do an automatic triangular mesh generation. It'll look really nice, and if you really look closely, you'll find that almost all of them are equilateral triangles. Okay. This is something we've talked about. The more explicit the equation, and this goes hand in hand with how far away from equilateral triangles you are. Okay. You get poor convergence. Degree of explicitness will depend on how large the skew source terms are. If the mesh is badly skewed, convergence will be poor. We know that already. Okay. See, here's the thing I was talking about. Partial convergence earlier on. The thing is, if you use CG, for example, CG is like a black box. Okay. You get some CG solver from somewhere. What you're going to do is you're going to feed in the A matrix, and the right-hand side vector will give you back a solution. Okay. Now, while it is solving internally in CG, you can't change anything. Your coefficient matrix and source terms are fixed. Okay. So now suppose you do CG and you do 200 iterations. After 200 iterations, you have to update your vertex values and redo the calculations. So why do even 200 iterations? So this is where people would use partial convergence. They would use CG for, let's say, converging the equation by 1 order of magnitude or half an order of magnitude, or maybe they will say, I just want to do 10 iterations. Then they would update the skew sources and then continue from there. Okay, so it leads to the concept of what's called inner and outer iterations. Okay, so if I draw a block diagram, okay, so here's your CG solve. This has what are called inner iterations, which are the iterations of your linear algebraic equation solver. And then once you do your CG, you update phi vertex and skew sources. Okay, and then this goes back and solves it again. So there is an outer iteration loop which is going on in the same time. Okay, and your convergence is monitored at the outer iteration loop, because this is an approximated form of the equations you're solving right there because of the explicitness. Okay, now if you're using a pointwise solver, Gauss-Seidel, then of course it's easy to do. You can just say, okay, every 5 iterations update the values of phi. All right. Okay, so so now we are going to do this in 3D. Okay, so far the derivation that I just showed you, this equation here, this is all 2D. It's not even valid for 3D. Okay. So the question is, how do we do this in 3D now? Okay. Now here is where we started when we did our derivation in 2D. What we did was we took the gradient vector, we wrote it as grad phi dot n times n plus grad phi dot t times t. But now what we have is 2 tangents. Okay, we have 3 unit vectors, n, t1, and t2. All right, which are shown here, for example. So this is what I'm trying to show here. Is it may not be very clear, but what we are trying to show is this. I have the triangle, that red triangle. Okay, this is not a triangle obviously, but think of it as this surface. Okay, and then I have a point here and another point here. Okay, and you join the 3 vertices of the triangle to that point, you get 2 tetrahedrons on 2 sides. That's what's shown in the figure. Okay, so 2 tetrahedrons straddling a triangular face, shown in red. All right, the star shows the face center of that triangle. Okay, and the 2 black dots are the centroids of the 2 tetrahedrons. Okay, on the 2 sides. And the n vector is the surface normal that's pointing out of the face. Okay, now it could be pointing the other way, but in this case, let's say it's pointing out of the face. Okay, and the tangents that are shown are basically along the edges of that triangle, 2 tangents. Okay, so everybody understand the geometry here? In 3D, it's kind of difficult to often understand what's really going on, but that's the basic idea. Okay, the reason we work with tetrahedrons again is because that way first of all you're guaranteed that it's a convex polygon. Okay, and secondly, this is the basic elemental shape in 3D, just like triangles are in 2D. Okay, now the problem is we can write this decomposition only if we guarantee that the 2 unit tangents are orthogonal to each other. Okay, so n, t1, and t2, if they're orthogonal to each other, then basically what I've done is I've defined a local coordinate system, and I can write it this way. Otherwise, I can't write it that way. Okay, I have to do a coordinate transformation otherwise. So now the problem is, if you try to think about, okay, what are my t1 and t2? The problem is that t1 and t2 may not always be perpendicular to each other, because the only way you can calculate t1 and t2 is by simply joining those 2 vertices and calculating that vector. Okay, I can't draw an arbitrary t1 and t2 on that plane and calculate it. It's very difficult to do. Okay, the only way I can do that is by joining the edges and calculating those 2 vectors. Okay, and that way there is no guarantee that they will be orthogonal to each other. Okay, so we have to find a different way of decomposing this gradient vector now, because we can't use t1 and t2 since they're not orthogonal. So here is what we are going to do. We are going to use a vector relationship. This is a different one. Okay, so here we are saying grad phi, the first term is the same, and then the next term uses this cross product relationship. Okay, this is just a vector identity. So instead of writing it this way, we now have written it with one term, but it involves cross products. Okay, so that's our starting point now. This term actually includes the contribution of both tangents. Okay, but it's written in terms of the normal. That's the good news. So now what we are going to do is do the same thing as we did before. We are going to dot it with that L vector, okay, all three terms. That L vector is, as I said earlier, is the vector joining these two guys, okay, the two centroids. So there it is. Okay, we've derived this already. Grad phi dot L is approximately phi1 minus phi naught. Okay, so same derivation as 2D because that was done in a vectorial sense. Okay, so we're just using that, and then we are going to define this delta, which is the n dot L, which is basically this distance, the distance between the two centroids in the direction of the normal. Okay, it's kind of hard to see here in 2D, but that's what that is. So if we do that, then our first term is just like in 2D, phi1 minus phi naught over delta. The only big difference is the expression for this tangential flux. Okay, that becomes that. So now the big question is, how do we evaluate that tangential flux term in terms of the cell center values of phi? Okay, so bear with me and try to follow this. I know this is a little bit complicated, but I'll try to go slowly and explain this, and if you go over it one more time at home, I'm sure you'll follow it, because there are no really tricks here. It's just direct application of some mathematical rules. All right, so what I've drawn here is that triangle that you just saw on the previous page. Okay, this triangle in red. What I've drawn is, for simplicity, I've just projected it on the plane of the paper and drawn it like a flat triangle. Okay, like that. So you can see now the surface normal is coming out of that plane, okay, which is shown here, right there. Okay, that's your surface normal. And then it has three vertices, A, B, and C, just like before. All right. And I have labeled these edges of the triangle 1, 2, and 3 in Roman letters. Okay, and those normals that you see, N1, N2, and N3, what they are surface normal, or I shouldn't call them surface normals, they're edge normals. Basically, they are perpendicular vectors to these edges, but they lie on the plane of the triangle. Okay, if you take a line, let's say, okay, a line like this normal can be any which way, right? So you have to decide what plane do I want to put it on. So my line is on that plane, so this normal is also on that plane. Okay, so it's perpendicular to this line. Okay, so here's a line, the normal is perpendicular, but on that plane. Okay, so that's what those are indicating. They're normals to those edges, but on the plane of the triangle. Okay. So now let's take a vector Q, and I'm going to define that vector as phi times I, let's say. Okay, I being the unit vector in the x direction. So if I calculate divergence of Q, then here's my divergence operator, dot product, phi times I, that gives me d phi dx. Okay. If I do an area integral of d phi dx dA, so I'm now integrating over the area of the triangle, imagine, okay, of this quantity. I can write it as, since d phi dx is equal to divergence of Q, I can write it as divergence of Q dA. Okay, and now using Gauss divergence theorem, the area integral reduces to a contour integral over the perimeter of the triangle. Okay, just like we did from volume to surface integral, now we are going surface integral to line integral, dimension reduction, Q dot the edge normals dl. Okay, so dl is basically a differential length along the edge of the triangle. All right, I bring back my q, which is phi times I. That's what I defined it as. So this becomes an expression for d phi dx integrated over the area. Okay? Everybody follow that? So this is again application of divergence theorem, but in 2D instead of in 3D. Right? So this is what we just derived. I'm rewriting it. So now what we can say is, okay, if I use the mean value theorem, then I can say this guy is nothing but the average value of d phi dx at the face times the area of the face. Because average of any quantity over an area is 1 over area times integral over the area. Right? That's the area average definition of any quantity. So here what I'm saying is, if I think of d phi dx as the average value at a face, then I can write this integral as the average value at the face times the area of the triangle ABC. Okay? Now, the perimeter of this triangle is composed of a summation over the lengths of its 3 edges. So this integral I can write as summation over the 3 edges. Okay? Phi becomes phi at the average value of phi at the edge. Okay? And then I dot ne is I dot ne. dl simply becomes the length of the edge. Okay? So we're summing over, we're replacing the integral by a discrete summation over the faces. All right? Everybody with me so far? So d phi dx at the face, okay, which I wrote as this guy. So this is basically d phi dx at the face times area at the face. Area ABC is nothing but area of the face. Okay, so therefore that becomes 1 over area ABC times this guy, which I got from here, and area ABC, as I said, is the same as the area of the face, and then you have this quantity. All right. So that's my d phi dx at the face. Similarly, I can write an expression for d phi dy at the face. All you need to do is, if you go through the derivation, replace the I by j, right there. Okay. If you do d phi dz, you replace the I by k. Okay. The derivation will follow exactly what we have done here. Instead of using q is equal to phi I, if you start with q equal to phi j or phi k, then you get these two expressions. All right. So my grad phi at the face, which I'm trying to approximate, is d phi dx I plus d phi dy j plus d phi dz k. I now plug in these 3 expressions that I just derived into that expression. Okay. So I have that times I plus that times j plus that times k. Okay. The 3 components I've replaced by those summation formulas that I just derived. All right. Notice each one is a summation over the 3 edges. So I can pull the 3 summations together, okay, and write it that way. So I've combined these guys. I still have a 1 over area f, okay. I still have a phi e and a le in each of these terms, as you can see. So that comes out as a common term. And then the rest is I dot ne times I plus j dot ne times j plus k dot ne times k. Okay. Now what is this? This is really the x component of the surface normal or the edge normal. This is the y component of the edge normal. This is the z component of the edge normal. So essentially what I have here is nxi, nyj, and zk, which is nothing but the edge normal itself. Okay. So gradient of phi is this quantity. Even outside of this finite volume formulation and so on. Okay. If somebody asks you, somebody gave you a problem where he said, okay, here is a distribution of phi on some arbitrary area. Okay. So suppose I take this surface and I say, okay, here are the values of phi at the different locations. I have made a mesh out of it, and I am giving you the values of phi in each location. And somebody tells you, tell me the gradient of phi at that point. Okay? If it was a nice Cartesian mesh, you would say, well, I'm just going to take these 2 points and get my d phi dx. I'm going to take these 2 points and take my d phi dy, and I'm done. Okay? Not so if it's an unstructured mesh. So what you have to now do is figure out a way to calculate the gradient at that point. This is what that is. Okay? This is telling you that the gradient of phi can be calculated using the divergence theorem, using simply that relationship. Okay? So here was our expression for the tangential flux, going back again to our original formulation. I'm going to take this expression right here, plug it in right here. All right? So that's what I get then. So straightforward substitution. All right? One thing you have to pay attention though is, and this is very important, is where you put these brackets when you do triple cross products. Okay? You can't do this. That's wrong. Okay? A cross B bracket cross C is not the same as A cross bracket B cross C. They are not commutative. Dot products are, cross products are not. Okay? So you have to be careful. So I'm carrying through this square bracket, as you can see, from the previous expression. Okay? Now this guy here, NF, this is independent of the summation. This is a summation over the edges. Remember, our edges were these guys, 1, 2, and 3. Okay? NF was this surface normal coming out of that triangle. It has nothing to do with this summation. Okay? So I can arbitrarily insert this into that summation. Okay? So that's what I've done here. Inserted that in here. Same thing for this guy. Inserted that in here. But you still have to be careful with the order now. Okay? Again, notice these two brackets here, which means this operation I'm going to do first and then follow it up with that, which is the same as the way it's done here. Okay, this cross product is done first, followed by that one. Okay? So here's a triple cross product, and here's a nice vector identity that converts cross products to dot products. Okay? So we take that, we plug it into this expression here, right here, okay? And this is what we end up getting. So the AB, whatever their corresponding values are, and this is what you get. Now, very nice things start happening once you plug it in. Number one, you see that NF dot NF is 1. NF dot NE is 0. Why? Because, as we said, let me just go back to the figure instead of drawing it again and again. Here it is. Okay, this surface normal, this guy, is coming out of the plane of that triangle. Those other three surface normals or edge normals are on the plane of the triangle. So by definition, their dot products are 0. Okay. So once I get here, this is 1, that's 0. Okay, and so my expression reduces to just this part with 1 substituted in there, and I get that. Right? So here's my JT now. The tangential flux expressed in terms of edge values of phi. This is even one step away from vertex values. Okay? So we'll get to that in a moment. Now, one of the challenges here, now suppose I want to write a computer program to calculate this. One question you have to ask is, what are your edge normals? That's a big issue because we don't know what the edge normals are. We've never computed it. Okay? So Now, before we go there, let's talk a little bit about what happens to this term. So one of the things I'm saying is if the L vector and the surface normal NF are co-aligned, again getting back to the same thing, okay? The L vector is the one connecting the two cell centers. If that's co-aligned with the surface normal, okay, like you would have in a Cartesian mesh or equisized tetrahedrons, then what you are going to get is, since L is co-aligned to N, okay, and NF and NE are perpendicular to each other, this quantity will be 0. Okay, because L and NF are co-aligned and NF and NE are perpendicular to each other. So this quantity will be 0 and the tangential flux will disappear. Okay, so again, if you take a three-dimensional Cartesian mesh and do this calculation, you should automatically find it comes out to be 0 as a test for your code. All right. So this will happen for hexahedral brick mesh or 3D tetrahedral mesh with faces of equal area, equisized tetrahedrons, basically. Okay. All right. So getting back to this issue of how do I calculate that? It's not known. All right. So what we make use of is this formula here. NE is equal to the unit tangent crossed with the n vector. So again, going back to that figure that I had, okay. So this vector, so again, think of it this way. I have a triangle, or let's take this quadrilateral, okay. This is my vector NE, which is the edge normal, all right. Here's my vector NF. Okay, NF is perpendicular to this face, NE is like that. All right, tangent is like that to that edge. Okay, so if you think about it, this vector crossed with that vector, what will it give you? It will give you a vector in that direction. Okay, so it's that vector crossed with that vector. If I do a cross product, it will give me a vector perpendicular to both of those vectors, which is basically the tangent at that edge. Okay, so that's what this relationship was showing. Okay, right here. So again, this tangent will be this vector crossed with whatever is coming out of the plane. All right. So if I plug that in there, instead of NE, plug that expression in there, okay, right there, and now I can do some manipulations. Now TE is the length of that edge times the unit tangent of that edge, okay. So this LE times TE right here is nothing but the actual tangent at that edge with the full length, okay. And we simplify that and we use another vector identity. So what we are doing is we are taking that right hand side and instead converting it to this side, okay. So same form as this form here, we want to convert it to that way. So we write it as TE dot NF cross L instead of TE cross N dot L, okay. And you will see it in a moment why we do that. So this quantity here is really independent of these edges. Okay. So what does that mean? That means I can compute it only once and then do this summation first and then do the dot product with that quantity. Okay, as opposed to computing this. If you think about computing this you have to do for every edge, okay, which is pretty tedious because that's a cross product. Cross product calculations are pretty expensive, okay, because it's really calculating a 3x3 determinant every time. Okay, so this calculation is pretty expensive. By using this relationship, we have converted it to a form where we don't have to do it for all three edges or however many edges that face has. We're just doing it once. All right. And in fact, you know, at one point I used to have a code where I was doing this, and then one of my graduate students said, "You're stupid. This is not the way you should do it." Okay, so he actually came up with this, one of my very early graduate students, later on went on to do a PhD in computer science, unfortunately. But he was the one who came up with this idea that if we can invert the position of these, okay, then you need to do it only once. So very nice innovation, so to speak. Now, the edge values, these guys are typically calculated by using the average of the two vertex values. Okay, that's the common way people do it. So, because this is the really the value at that edge, and so you just take, the average of those two values. So once you do that, then this is your final formulation. Here's the edge value, which will have two vertex values. Then this guy, you just compute it once, and then this is your implicit term, this is your source term. So again, this whole thing is your skew source summed over all the faces. Okay. So that's your final summation, summary, 2D equation and 3D equation. The expressions are slightly different. This one, as you can see, is slightly simpler. Here you have to do more calculations in 3D. All right. But other than that, so if you think about a 2D code versus a 3D code, and you're generating one for an unstructured mesh, really the only thing you have to do is you have to say that, okay, if 2D, then this is how you calculate your skew sources. If 3D, then this is how you calculate your skew sources. Everything else is the same. These terms are identical. Okay, you don't even have to bother about 2D or 3D for those terms. Okay, so any questions?